Technomaths. So today we have taken the question what will happen and what are the forces acting on a conductor where current is carrying through the conductor and conductor is placed in a magnetic field, right? So what are the force on a current carrying conductor in a magnetic field? This is basically the thing which we are going to discuss, right? Force on the, we'll see what are the force acting on a current carrying conductor. Force acting on a current carrying conductor. And when this conductor is placed in a magnetic field, the condition is that it is placed in a magnetic field. So my dear friends, I hope you have the basic understanding. Whenever the current is flowing through any conductor or wire, certain magnetic field is generated around it, okay? And the direction of that magnetic field is given by the right hand thumb rule. If the conductor is lying on the plane like this, and if you are knowing the direction of the current, right, if this is the direction of the current, then just apply the right hand thumb rule, okay, just holding this conductor. If the conductor is like this, just hold it. If you hold it, the right hand thumb rule will apply over here. This thumb will show the direction of the current, right? Right hand thumb. So that means right hand, this is my right hand, and the thumb of my right hand will be into the direction of the current, right? Then you can see a curl is happening. You can see from my fingers a curl is happening, okay, when the direction of the current is like this, you can see, right? And this curl is just initiating from here and going into this direction, isn't it? Then this will give the direction of the magnetic field. This will be the direction of the magnetic field represented by B. Now you can see why the direction is into the anti-clockwise direction, right? Direction of B, why the direction of B is in the anti-clockwise. So my dear friends, let us understand. If this is the current which I said, if this is the direction of the flow of the current, you can see this is the direction of the flow of current from right to left, right? Then the point of this pen is pointing into that direction. Now hold that pen, mark your thumb into that direction. This will give you the direction of the current. So thumb will be given by the thumb will give you the direction of the current. Thumb will give you I, which is your current, right? Thumb is given by I, which is your current. Now this curl will give you the direction of the magnetic field. You can see this magnetic field when you see above the top of this wire. This is electrical wire. This is an wire, or you can say conductor, right? This is a conductor, and here you can see this is entering inside the page. So that's why just make a mark cross. That means it is entering inside the plane of this paper above the conductor. And when you just hold it like this, hold it, you can see these fingers are coming out, the fingers are going below the pen and then coming out. You can see this portion, right? So this is coming out from here. This is coming out. That means here you can see this is coming out. This is coming out, right? So we can say that yes, the direction of the field, magnetic field, will be like this, right? Out of the plane of the paper. This is the direction of B, magnetic field, right? My dear friend, this was the case when the conductor is generating the magnetic field due to the flow of the current, right? Now we will study what is the Fleming's left hand rule and how it is applied when a conductor is placed in a magnetic field. What are the force on a current carrying conductor in a magnetic field, right? So this we discussed earlier. Okay, now go to the second part. Okay, this one. So here we will be applying the Fleming's left hand rule, right? How it will be applied, you can see. If you have seen a question given into the NCERT, okay, the experiment is that if a conductor is like this, if a conductor is like this, right? If the conductor is like this and this is having hanged like this, a current is flowing from here and exiting the conductor like this, okay, and this is hanged through a wire, okay, and the wire is just wrapped around it and going into the top, right, and through this it is making a circuit like this, whose negative terminal is here and positive terminal is like this, okay. Now this is also hanged through here like this, right? So current is coming into this way, right? Let us see this arrangement is happening. Okay, I'm not showing that a stand and everything. What I want to say, what is the application of Fleming's left hand rule? What is the applications of Fleming's left hand rule into deciding the force current on the current carrying conductor in a magnetic field, right? So if this is plus, the current will go from this direction, this will flow like this, and mind it, this is a conductor, okay, this is a conductor, current carrying conductor, we can say like this, right? Now our experiment is like this. When this, what are the forces acting on this, okay, what are the forces acting on this, and this is having placed into a field of magnet, what is the field of magnet? The field of magnet is like this. A horseshoe magnet is like this, okay, which is placed over here into the plane of the paper, okay, and the you can see the terminals over here, okay, this is north and this is south, right? So my dear friends, what is happening over here, try to understand, okay. So first of all, north to south, the magnetic field will be like this, north to south. This is north, this is south. So this will be the direction of the magnetic field represented by B, right? You can see here north to south. And this current is not into the same direction of this magnetic field, mind it. First of all, what are the three things which is explained into this Fleming's left hand rule? Try to understand. One is force, another is current, and third item is magnetic field, right? So what does Fleming's left hand rule said? When the direction of the magnetic field is known to you, then use your left hand like this. Use your left hand. Okay. So use your thumb stretched like this. Use your finger stretched, and use your third finger stretched like this. Okay. So this will give you the forefinger. The first finger will give you the direction of magnetic field, and the middle finger, which is just in perpendicular to that one. All the three fingers should be perpendicular to each other. Then this will give you the direction of current, right? Like this. See this. This is the this is the forefinger. After thumb, this is the forefinger giving you the direction of magnetic field. So this is happening over here, right? Now from here you can see this. You just stretched it, and you can see first, second, and third. This is the third finger, which is, it will just, you can see this is angle of 90 degree between. This is the direction of B, and this will be the direction of current current, and this is making an angle of 90 degree. And if you see the thumb also, this is also making an angle of 90 degree, right, with the magnetic field, this one. So Fleming left hand rule said, when you just stretch your thumb, forefinger and middle finger, then B will be given by your forefinger. The direction of magnetic field is given by your forefinger, and the middle finger, which is stretched at an angle of 90 degree towards it, is given by the gives you the direction of, middle finger will give you the direction of current, which I am representing by I. This is represented by, this is given by the middle finger, and this is your forefinger. Now if you have seen it, the thumb is perpendicular to this forefinger. This is making an angle of 90 degree. This will be the direction of the force, my dear friends. So just simple consider like this, that if this is x-axis, right, if this is y-axis, right, then the direction of z, which is coming out of the plane of the paper, like this. This is coming out of the plane of the paper here. This will give you the direction of the force, right? So this one will give you the direction of the force, and that will be represented by your thumb. Thumb of what? Left hand. That's why the name is Fleming left hand rule, right? Left hand rule. That's why I've used my left hand to show you the direction. Okay, you can see, just stretch your forefinger, stretch your middle finger. This will give you the direction of magnetic field. This will give you the direction of current, right? Now you can see this angle of 90 degree over here. This is y-axis, this is x-axis. So this is x-axis gives you the current, the middle finger. The forefinger gives you the direction of what? Magnetic field, and this will be the force, right? This will be the direction of the force, right, which is just perpendicular to the x and y axis. This is into the z direction. Let me write it like this, Z. And this will give you the direction of force. F is force, right? Now, my dear friends, we can see what is the direction of the force which is happening over here into the current. You can see this is the magnetic field. So magnetic field over here into this example, you can see what is the direction of the force which is happening. If the magnetic field is like this, because this magnet is placed like this, okay, on the paper, then the field will be from north to south. Field will be generated from north to south, right? This will give you the direction of magnetic field. Now just apply the Fleming's left hand rule. So here is the direction of north to south, is the direction of the magnetic field into this question, into this experiment. And conductor is just standing perpendicular to it. This conductor, if I am not able to explain the figure because this is two-dimensional, this conductor is, you can see, standing over here like this, coming towards the camera, right? So here you can see this is I is like this. The current is into the direction like this. Current is like this. Okay. Now, if the direction of the current is like this, which is perpendicular to the direction of the magnetic field, that you need to understand, because the current will, for the whole magnetic field, current is always acting perpendicular to it into this case, because this is the direction of magnetic field. This is the direction of magnetic field. This is your B, right? Now, what we want to understand or explain over here, what I want to explain, that if this is the direction of magnetic field, this conductor is standing perpendicular to the direction of the to the plane of the paper like this. Then use the Fleming's left hand rule to calculate the force acting. Here you can see this is the B. B, that means north to south, this magnetic field is there, right? And the current, direction of the current is from left to right, but here the direction is current from right to left. So just adjust your left hand in such a way that it will suits the direction of magnetic field and current. So just reverse it. When you just reverse your hand, you can see this, that yes, the current should be coming out of the plane of the paper, right? So this will be happening when, like this will be happening only in this condition, because this is the direction of magnetic field which is happening over here. This is the finger, middle finger, you can see. This will give you the direction of the current, because this conductor is hanging over here and it is just standing perpendicular to the plane of this magnetic field. So that's why you can see the direction of pen. This will give you the current. Then what will be the direction of force? This one, the thumb. So thumb is pointing towards left here. So you can see this will be the direction of force observed. This will be the direction of force observed on the conductor. So that's why this conductor is shifted towards left. This conductor will be shifting towards left, right? And when you just observe it, so that means if B is there, I is perpendicular to this, as per the Fleming's left hand rule. If the direction of B is there and I is into this direction, which I have considered out of the paper, right, then definitely the force will be acting towards left, right? So you can see the current is like this here, out of the paper. Okay, so the deflection of the conductor is towards left, right? So you can see if B is like this, not to south, right? Current outside, that means into the, if you consider x y z, y here, let me see, if you consider into the x y z direction, right? If this is xyz, then y axis gives you the direction of B, right? Y axis gives you the direction of B. This will give you the direction of magnetic field, and this z direction, right, will give you the direction of current. But you can see, if you apply the Fleming's left hand rule, if you apply that Fleming's left hand rule like this, you can see the direction of the thumb will be pointing towards left, right? So negative x direction, so the negative x direction will give you the force acting into this situation when the current is flowing into the direction as shown to you, right? And this is the direction of into the positive z direction. This is the direction of, so this will be given like this. Okay, so that means if magnetic field into the positive y direction, as you can see over here, magnetic field into the positive y direction into the xy axis, and current is coming out into the plus z direction, right? This is plus z direction. This will be, this is given by your, this is the direction of the current. Then negative x will be your direction of force by the application of Fleming left hand rule. You can just see, you can just set your forefinger into the direction of magnetic field which we put it. Current is coming out of the plane of the paper, so this will be the middle finger coming out. You can see this conductor, the current is coming out like this, like this. So this will give you, now the thumb is pointing towards left. You can see, if all of these three fingers and thumb, two fingers and thumb into the 90 degree to each other, you can see this is 90 degree, this is also 90 degree, and this middle finger and thumb is also making an angle of 90 degree. So this will give you the direction of force into the negative x direction. Negative x direction, that means if you consider this entire figure like this, if this is plus x, if this is plus x, then definitely this will be minus x, right? This will be plus y, right? And the plane out of this is plus z. So that's why I tried to explain it. Into the plus z direction, current is there. I current is there, right? Magnetic field is there into the y direction. Magnetic field into the y direction. Just see this. Why I want to explain through the xy axis and z axis, so that you can understand it easily, right? So that you can understand it easily. This is z, which is generally used for the three-dimensional plotting, right? Z, and this is x, negative x, into the minus direction, x, and this is plus x into the right hand side. So my dear friends, if this is the direction of magnetic field and the direction of the current is coming out of the plane of the paper, then the force exerted on this conductor is towards left, right? The force will be towards negative x direction, right? So this is depicted only by application of Fleming's left hand rule. What Fleming's left hand rule says, that these three items, that means forefinger will give you the direction of the magnetic field, middle finger will give you the direction of the current, and the force will give you the direction of, will be given by the direction of your thumb, right? When all these three items are, all these three fingers are kept stretched and making an angle of 90 degree with each other. This is 90, this is 90, and this is also 90, right? Make sure. So my dear friends, in this way we can see application of Fleming's left hand rule is applied over here, and how the deflection will happen. Now my dear friend, just into this experiment, if you want to observe, just change the direction of the current. If the direction of the current is coming into this way, right, change the direction of the current, just change this battery terminal, then this will be plus and this will be minus into the second time, right? Earlier it was minus, but now make it a plus, this terminal, and this make it a minus. When you just change the terminal of the battery also, then the deflection will be changed, because you can see the direction. If this will be the plus, the current will be flowing like this, and this, in this conductor the current will not come from top to bottom, but it will go from bottom to top. So it will be just going like this, okay? When the current will be going like this, then into this Fleming left hand rule, when the direction of current was coming out of the paper, this will go inside the paper, isn't it? This will go inside the paper, and when this will go inside the paper, you can see here, just apply the Fleming left hand rule, this middle finger going inside the paper, right? Then you can see the thumb is pointing towards right. Then the force which was acting towards minus x direction, the direction of the force will be changed, and now it will be acting towards plus x direction. Only in the case the battery terminal is reversed, right? So you can see how the change in the battery terminal, or this will change the direction of the flow of current, and this will change the application of force from negative x direction to the positive x direction, right? So you need to understand how the batteries or the current is impacting the magnetism or the force acting on this conductor, which is suspended like this, which is hanged or kept perpendicular to the plane of the paper, right? Similarly, it will happen when you just change the magnetic field also. If the magnetic field is here north pole, here south pole in the horseshoe magnet, right? If you just change the direction of the magnetic field, that rather than keeping north over here, just put north over here, then the direction of the magnetic field will be not like this from bottom to top, it will not move, but it will change from top to bottom. Now again use the Fleming left hand rule, okay? And keep other things as common, current as like this. Just keep current clockwise as it is happening, positive terminal into the right, negative terminal into the left, current is flowing like this into the direction which is shown, right? Then current is coming out of this conductor is kept perpendicular and current is coming out of this plane of paper, right? So just put up this direction, put up, just arrange your forefinger into the direction of magnetic field, arrange your middle finger into the direction of current. Now current is coming out, that's fine, and direction of magnetic field is not from bottom to top. It's again, as I said, north and south is changed into the second case. If north instead of south, it will be north here into the second case. And then this north will become south. Then the direction of magnetic field will be like this from top to bottom, isn't it? If the direction of the magnetic field is changed to this into the second case scenario, then arrange your finger. So you can see this will be happening. How this will be happening? Earlier it was into the direction of magnetic field. Now just change this. If you change this, magnetic field will be like this, then current perpendicular to it coming out of it, right? Then what will happen? Just try to do it. Try to do it. Just try to do it. Magnetic field, this point will be giving going towards south and this is north if you are considering. Then just you need to arrange it like this. So this should be like this, okay? And current coming, this middle finger, current is coming out of the plane of the paper. Then you can see this thumb is going from into the plus x direction, you can see here. Then into this case, if the pole of the magnet is changed, then force will not be acting towards left, it will be going towards the right direction, that is plus x direction. This will be the direction of the force now. So you can see how if the magnetic field is changed, how the direction of the force is changed on the conductor, right? So my dear friends, we have understand what is Fleming's left hand rule today, and what is the application of this Fleming's left hand rule, and how to find the direction of the field, magnetic field or current or the force acting onto that conductor when magnetic field is changed, when the direction of the current is changed, how these three items are related with each other. One is magnetic field, what is the direction of the force, and what is the direction of the current. If you do any deviation into one of the item, the another one will be deviated, and all this will be followed by the Fleming's left hand rule. Okay, and the Fleming's left hand rule shows that the thumb will be given by the direction of your thumb will give you the direction of the force, current will be given by the direction of the middle finger, forefinger will give you the direction of the magnetic field, right? So with this we are winding up today's session, my dear friends. Take care, happy learning, bye bye, thank you.